Hello friends, in the previous video we have seen how to calculate change in length for member in series and for composite section means member is in parallel. See, this is your one more important topic, that is thermal stress, or you can say the temperature stress. When the expansion or contraction of the member due to temperature variation is prevented, then the stresses induced in the member is called as temperature stress. See in this figure, this is the initial position. You can see from A point to B point. The length is given, you can see the length. When the temperature is rises, the stresses induced in member are in compressive in nature. When temperature falls, the stresses induced are tensile in nature. See, you can see this diagram. See, this one is A to B. This is the free expansion. There is no stress. B to B dash, that is free expansion. See, you can see the formula alpha into T into L. This one is the entire length. So you can see this diagram. Here the restriction is there. See, A to B point. This one is L. Expansion prevented, stress induced. So in this case, the stress will induce. See, we know that Young's modulus is equal to stress upon strain. Here, the strain is temperature strain. So here, ET is equal to change in length prevented upon original length. See, this is the length prevented, change in length prevented. That is alpha into T into L. So here you can see the formula L into alpha T upon L. But Et is equal to alpha into T. So here the formula is stress is equal to Young's modulus into alpha T. Alpha is the coefficient of thermal expansion in degree Celsius or in degree Kelvin. T is the temperature variation in degree Celsius or Kelvin. E is the Young's modulus. Sigma is the stress induced due to change in length prevented. The formula is very important. Please highlight this formula. While referring every video, please see in e-content. E-content will help you to understand each and every concept. Highlight this problem. Highlight this formula. Temperature stress in members in parallel. Conditions are very important because according to the condition we will solve the problem. See this diagram. This is the initial position. First material, that is steel. See the another material, that is copper. That is the second material. Here you can see X1 and X2. That is free expansion due to temperature. You can see the diagram. And this diagram, this one is a steel, this one is a copper. Here the nature is away from the body. Here the nature is towards the body. T is given. You can see this dotted vertical line here. Then you will get this one more vertical line. For steel, that is alpha into T into L1 for steel. Here you can see the alpha into T into L for copper. This distance is X1. This distance is X2. Here you can see expansion prevented for equilibrium. You can see this is the delta L. Expansion prevented for equilibrium. This is the third diagram. Diagram is very important. to understand this concept? See, a composite member formed by joining a steel rod and copper rod as shown in figure. See here, already I shown you, this is a steel and this one is a copper. If both the materials are allowed to expand freely, then change in length of copper will be alpha copper into T into L, and for steel that is alpha for steel into T into L. See here, alpha copper into T into L is greater than alpha of steel into T into L. See, you can refer this diagram for that. See this. This is for copper. This one is for steel. So according to the diagram, this condition is very important. When equilibrium is reached, the tensile force is exerted by copper on steel will be equal to compressive force exerted by steel on copper, already shown in the diagram. For composite section, final deformation is same, that is also shown in the diagram. If alpha 1 is greater than alpha 2 and the temperature rises, then compression in material 1 is equal to tension in material 2. So sigma 1 into A1 is equal to sigma 2 into A2. Total elongation of steel is equal to total elongation of copper. So you can see the formula alpha into T into L plus PL upon AE for steel. Here in bracket alpha into T into L minus PL upon AE for copper. So the formula will be, we know that sigma is equal to P by A. So stress upon E1 plus stress upon E2 is sigma 1 upon E1 plus sigma 2 upon E2 is equal to alpha 1 minus alpha 2 into T. The condition is very important. Alpha 1 is greater than alpha 2. And the total strain is equal to E1 plus E2 is equal to alpha 1 minus alpha 2 into T. So change in length, that is deformation, is equal to alpha 1 into T into L1 minus sigma N1 L1 upon E1 is equal to alpha 2 into T into L2 plus sigma 2 L2 upon E2. Here you can see the first case the sign is given minus, in the second case sign is given plus. According to the diagram, you can see this is a copper material, this one is the steel material. According to the diagram, according to the condition of member in parallel, that is composite section, the formulas are given. Please highlight this formula for total strain and for deformation. We have to use this formula while solving the problem. See this diagram very carefully. The another type, that is composite member in series. You can see A to B, B to C is there. So E1 and E2 is the Young's modulus for first portion and second. Alpha 1 and alpha 2, that is coefficient of linear expansion in 1 and 2. Just I am showing you the conditions. Free expansion is equal to alpha 1 into T L1 plus alpha 2 into T into L2, that is first equation. That is very important. Deformation due to reaction, that is, you know the formula of deformation, that is PL upon AE. Here deformation due to reaction, that is sigma 1 into L1 upon E1 plus sigma 2 into L2 upon E2. Already we know the formula. This is the equation for compatibility. free expansion is equal to deformation due to the reaction. So free expansion is equal to alpha 1 into T into L1 plus alpha 2 into T into L2 is equal to sigma 1 into L1 upon E1 plus sigma 2 into L2 upon E2. If supports are yield, then there will be a change in formula. Free expansion due to temperature minus gap is equal to deformation due to reaction. So formula will be alpha into T into L1 plus alpha 2 into T into L2 minus gap is equal to sigma 1 into L1 upon E1 plus sigma 2 into L2 upon E2. So different numericals are there. The first type, that is temperature stress and strain on uniform bar. Second, temperature stress in member in parallel, that is composite section. And next member is in series. See the important formulas. Delta L is equal to alpha into T into L. Temperature strain E is equal to delta L upon L, nothing but alpha into T. Temperature stress is equal to small e into capital E, that is alpha T into E. Ends are yielding free expansion, that is delta L is equal to alpha into T into L minus gap. Temperature strain E is equal to delta L upon L. If the condition ends are yielding, then alpha into T into L minus gap upon L, and temperature stress sigma is equal to E, small e into capital E, that is strain into Young's modulus. See, this chart is very important to solve the problem. Highlight each and every formula. Here just I am taking 1, 2, 1, 2 problems. See the problems from May 2012 for 10 marks. A steel rod of 30 mm diameter and 5 meter long is connected to two grips. The rod is maintained at a temperature of 95 degrees Celsius. Determine the stress and pull exerted when temperature falls to 30 degrees Celsius. If the ends do not yield, first condition is given, the ends do not yield. Second condition, the end yields by 0.12 centimeter. Take Young's modulus E is equal to 2 into 10 raised to 5 mega Newton per meter square, and the coefficient of expansion, that is alpha, is given, that is 12 into 10 raised to minus 6 degrees Celsius. So here you have to calculate pull in the rod, that is P. We know that P is equal to stress into area. So first condition, when the ends do not yield, before that you have to write given data. Diameter is given, that is 30 mm. Length is given, that is 5 meter. Temperature 95 degrees Celsius minus 30, because temperature falls to 30 degree. So 95 minus 30, fall of temperature, that is 65 degrees Celsius. Young's modulus is given in meganewton, so you have to multiply by 10 raised to 6. So value will be, you can see, 2 into 10 raised to 5 Newton per mm square. Conversion is very important. The value is given in meter square. You have to convert into mm square. So divide by 10 raised to 6. First condition, when the end do not yield. So to calculate temperature stress, that is sigma, is equal to E into alpha into T. We have the value of E, we have the value of alpha, we have the value of T. You will get a temperature stress, that is 156 Newton per mm square. So P is equal to stress into area. We have the value of stress and we have the value of area. You will get pull in the rod? Answer is 110,269.902 Newton. The second condition, when the ends yield by 0.12 centimeter, we know that temperature strain is equal to contraction prevented upon original length. So formula is alpha into tau T into L minus delta, alpha into T into L minus delta upon L. So we have the value of alpha, that is 12 into 10 raised to minus 6. We have the value of temperature, that is 65. We have the length, that is 5,000, and the gap, that is in mm, the gap is 1.2 mm. See, the value is given in centimeter. You have to convert in mm first. That is 1.2 upon 5,000. The answer is 5.4 into 10 raised to minus 4. 5.4 into 10 raised to minus 4, that is temperature strain. Now temperature stress is equal to temperature strain into Young's modulus. We have the value of Young's modulus. We have the value of temperature strain. So the temperature stress is equal to temperature strain, that is 5.4 into 10 raised to minus 4 into Young's modulus, that is 2 into 10 raised to 5 Newton per mm square. So the answer will be 108 Newton per mm square. So pull in rod, that is force, is equal to stress into area. We have the value of temperature stress. We have the value of area, that is pi by 4 into d square. So pull in the rod is equal to 108 into pi by 4 into d square. We have the value of d, that is 30. The pull in the rod in the second condition, there when the ends yield by 1.2 mm, the answer is 76340.701 Newton. See, just by using simple formulas, the conditions are very important. You can solve n number of problems. See, the similar problem is here for December 15, December 16 for 10 marks. See, a 4-meter long steel bar of a square cross section of 40 mm side is heated through 75 degrees Celsius with the ends clamped before heating. Calculate thrust exerted by the bar on clamps. First, the clamps do not yield. First condition, do not yield, and the second condition, yield by 0.6 mm. See, the Young's modulus is given, that is 200 GPa, and alpha is also given, that is 11.5 into 10 raised to minus 6 per degree Celsius. First case, we know that free expansion is equal to alpha into T into L. We have the value of alpha, we have the value of T, we have the value of L. You will get free expansion, and thrust is nothing but stress into area. Stress is nothing but alpha into T into E into area. We have the value of area. You will get the answer for first case for do not yield. For the second case, that is the thrust exerted on bar if the clamps yield by 0.6 mm. Just here the formula will be free expansion minus gap upon L. You have the value of free expansion. If you have the value of gap and the remaining terms are same, you will get the answer for the given problem. Second condition, see, thermal stress sigma is equal to E into means strain into Young's modulus. We have the value of strain, we have the value of Young's modulus, and we know that thrust exerted F is equal to stress into area. Here we have the thermal stress, we have the area. You will get the answer 228 kilo Newton. See, not need to explain each and every problem deeply, because previous problem is very similar to this. Just go through that. See, in the type 2, please refer this formula very clearly. It's a very important topic. Composite section, temperature stress in member in parallel, that is type 2. Already I explained you the formulas. but please write down each and every formula very carefully while solving. Formulas are very important. If alpha 1 is greater than alpha 2 and temperature rises, then compression in first material is equal to tension in material 2. So sigma 1 into A1 is equal to sigma 2 into A2. Total elongation of material 1 is equal to total elongation of material 2. So the formula is alpha into T into L plus PL upon AE for first material is equal to alpha into T into L minus PL upon AE for second material. We know that stress is equal to P by A. So strain in first material plus strain in second material is equal to alpha 1 minus alpha 2 into T. That is total strain, that is E1 plus E2 is equal to alpha 1 minus alpha 2 into T. Here you can see the deformation alpha 1 into T into L1 minus sigma 1 into L1 upon E1. Here again a deformation delta L is equal to alpha 2 into T into L2 plus sigma 2 into L2 upon E2. This is the condition for type 2 numerical, that is temperature stress in members in parallel, that is composite section. Here I am showing you the example on this condition, that is temperature stress in member in parallel. That is very important problem. Compound bar consists of copper rod 20 mm in diameter and steel tube 60 mm in external diameter with thickness 5 mm. The copper rod and steel tube are assembled coaxially and their ends are rigidly fired at 30 degrees Celsius. If the compound is heated to 130 degrees Celsius, determine the stress induced in each metal. So you have to calculate stress induced in copper and stress induced in steel tube. See, the values are given. ES is equal to 200 kilonewton per mm square. Young's modulus of copper is given, that is 120 kilonewton per mm square. Coefficient of free expansion, thermal expansion is given for steel 12 into 10 raised to minus 6 per degree Celsius, and for copper 18 into 10 raised to minus 6 per degree Celsius. Now here dimensions are given. Diameter of copper, small diameter of copper, that is 20 mm, capital, that is see for steel, that is 60 mm. We know that inner diameter of steel, because steel tube is there, so 60 minus 2t, thickness is given, that is 5. So answer is small d s is equal to 50 mm. You can see here T1 is equal to 30 degrees Celsius and T2 is given, that is 130 degrees Celsius. Young's modulus for steel is given, that is 200 kilonewton per mm square. E for copper is given, that is 120 kilonewton per mm square. Alpha for steel is given, alpha for copper is given. Alpha for steel, that is 12 into 10 raised to minus 6 per degree Celsius. Alpha for copper, that is 18 into 10 raised to minus 6 per degree Celsius. Just you have to find out the stresses induced in steel and stresses induced in copper. See, as per the given data, just see, this one is your copper tube having diameter 20 mm. This outside, that is steel tube. You can see the steel tube. You can see the front view as well as side view. Outer diameter of steel, that is 60 mm, shown in the diagram. Thickness, that is phi. So inner diameter, that is 50 mm. You can see the diameter 50 mm. 60 minus this phi minus this phi. Inner diameter, that is 50. By using condition, you have to solve the problem. Here you know that alpha of copper is greater than alpha of steel. So compressive stress produced in copper and tensile stress will produce in steel. These conditions are very important. Here we have the area for copper. Copper is a solid. So here the formula, solid circular bar. So formula is pi by 4 into dc square. You will get the area of a copper, that is 314.6 mm square. Area of steel, cross-sectional area of steel, that is pi by 4 into capital dA square minus small dA square. Outside diameter of steel, that is 60. Inside diameter of steel, that is 50. So the answer will be 863.94 mm square. Here the exact temperature rise, that is T, is nothing but T2 minus T1. So 130 minus 30 is equal to 100 degrees Celsius. See, till this point, each and everything as per the just regular process. The conditions are very important. Again, I am telling you, for the composite member, the conditions are very important. Here in this case, alpha copper is greater than alpha steel. So compression in copper is equal to tension in steel. We know that compression of copper is nothing but sigma into area for copper is equal to tension in steel is nothing but stress into area, stress for steel into area of steel. So here in this condition, we have the value of only area. So area of copper we have, area of steel we have. So the answer will be sigma copper, means stress of copper is equal to 2.75 sigma of steel. See, we don't have the value of stress of copper and we don't have the value of stress of steel. It is equation number 1. You have to highlight this equation because we have to find out stress of copper and stress of steel. But according to this condition, you will get this equation. This condition is very, very important. Please highlight this condition. It is very important condition to solve this problem. Using the relation, we know that strain in steel plus strain in copper is equal to alpha copper minus alpha steel into T. Here we know that the formula of strain, that is sigma S upon ES plus sigma copper upon Young's modulus of copper is equal to, in bracket, alpha of copper minus alpha of steel into T. Here we don't have the value of sigma S. So sigma S, stress of steel upon Young's modulus of steel, that is 200 into 10 raised to 3, plus we don't have the value of stress in copper, but we know that stress in copper is nothing but 2.75 into stress of steel. From equation number 1, you have to put 2.75 into sigma S, that is stress of steel, upon Young's modulus is given, that is 100 into 10 raised to 3. Here we have the value of copper, we have the value of steel, that is 18 into 10 raised to minus 6 minus 12 into 10 raised to minus 6 into T, that is a temperature, that is 100. You can see here that is a temperature. There is only one unknown, that is sigma steel. You can calculate the value of sigma steel, that is 18.46 MPa. The value is positive, so it is tensile in nature. After getting the value of stress of steel, you can calculate the value of copper by using first equation. So the stress in copper is equal to 50 into 50.77 megapascal. That is in compressive in nature. See here, compression in copper and tension in steel. So the first value of steel, that is tensile, and the another value is in compressive in nature. So many examples are there, but the conditions are same. You can solve each and every problem by using this simple condition. See, you can see the next problem, that is for May 11, May 15 for 10 marks. The conditions are same, only the data is difference, means change in temperature, Young's modulus will be different. The remaining things are same, conditions are same. You can solve n number of problems by using these formulas. Another type, that is member is in series. You can see this, that is very important. If supports are rigidly fixed, then the first condition, that is alpha into T into L1 plus alpha into T into L2 is equal to sigma L upon E1 plus sigma L upon E2. When if supports are rigidly fixed, that is, this is your condition. If supports are yielding, then the condition will be like that: alpha into T into L1 plus alpha into T into L2 minus gap is equal to sigma L upon E1 plus sigma L upon E2. Force exerted by supports are equal and opposite. That is third condition, that is member is in series. See, very important chapter. The composite bar, the another problem is the composite bar consisting of steel and aluminum components shown in figure. See, figure is given, is connected to two grip at a temperature of 60 degrees Celsius. Find the stresses in two rods when the temperature falls to 20 degrees Celsius. Conditions are given. If ends does not yield, and the another condition, if the ends yield by 0.25 mm. C. Young's modulus of steel is given. Young's modulus of aluminum is given. Young's modulus for steel, that is 2 into 10 raised to 5 Newton per mm square. For aluminum, that is 0.70 into 10 raised to 5 Newton per mm square. Alpha of steel is equal to 1.17 into 10 raised to minus 5 per degree Celsius. And alpha of aluminum is equal to 2 into 34 into 10 raised to minus 5 per degree Celsius. This problem is for 10 marks. See this diagram. Steel is given, that is third type. This one is aluminum. You can see cross sectional area is given, that is 250 for steel. For aluminum, that is 375. You can make given data in this format. See the given data. Steel bar area, that is 250. Length is given, that is 800. Young's modulus is given 2 into 10 raised to 5. Alpha is given, that is 1.17 into 10 raised to 5, or 10 raised to minus 5 per degree Celsius. Temperatures are given T1 and T2, that is T1 60 degrees Celsius, T2 20 degrees Celsius. For aluminum bar, area of aluminum bar, that is 375 mm square. Length, that is 400. Young's modulus of aluminum, that is 0.70 into 10 raised to 5 Newton per mm square. Alpha of aluminum, that is 2.34 into 10 raised to minus 5 degrees per degree Celsius. And you can see the T, that is 40 degrees Celsius. Difference between T1 and T2, that is 40 degrees Celsius. So according to the formula, just you have to put the formula, you will get the answers. We know that for member is in series, the first condition, ends does not yield. The expansion is equal to expansion prevented by supports. We have the formula alpha into T into L for steel plus alpha into T into L for aluminum is equal to RL upon AE for steel plus RL upon AE for aluminum. Already I have explained the formulas to you. We have the value of alpha of steel, we have the value of T we have the lengths. After putting all the values in this equation, the equation is very simple. There is only one unknown, that is R. So you will get the value of R. After simplifying this equation, you will get the value of R, that is 23.97 kilonewton. And we know that stress in steel is nothing but R upon area. We have the area. So stress in steel, that is 95.88 megapascal. Similarly, stresses in aluminium, that is R upon area of aluminium. The answer will be 63.92 megapascal. So there is only one change. If ends yield by 0.25 mm, free expansion minus gap is equal to extension prevented by supports. So free expansion, that is 0.7488 minus gap, that is 0.25. Prevented by supports, that is 3.124 into 10 raised to minus 5 into R. So there is only one unknown, that is R. Here you will get the value of R, that is 15.97 into 10 raised to 3 Newton. Again, calculate the stress of steel. For stress is equal to load upon area, cross-sectional area. We have the value of R, that is 15.97 into 10 raised to 3 upon area of steel, that is 250. The answer is 63.87 megapascal. Stress in aluminium, again to calculate stress, R upon area of aluminium, cross-section area of aluminium, that is 375. R is calculated, that is 15.97 into 10 raised to 3. The answer is 47.95 megapascal. See, in this video, we completed thermal stresses. The next video, we will see another topic from the same chapter, that is principal plane and principal stresses.